I'm going to present to you my PhD thesis titled Non-Negative Matrix and Tensor Factorization, Models, Algorithm, and Application. And about the talk itself, because the thesis has quite a lot of material, I'm not going to talk about all the aspects. I'm going to talk about only the interesting part. The first part is about minimum volume NMF. So before talking about that, first of all, why do NMF? These slides come from the slide I made previously. Basically, I will show this slide whenever I give a talk in MMF. That is, why do NMF? There are, of course, many reasons, but of course, for me now, the last one is the most important because this is cool. So that's the reason. So what is NMF? Basically, is a following task. Somebody asks you, say, they give you a data M, and of course the parameter R. Sometimes the R is not given, but let's say now it's given. And the task is very simple. They ask you to decompose it into W and H with some structure. This is the task. So you are given an input, you want to find output. So the task of NMF very simple. You design a model and an algorithm to achieve this goal. So that means you are given this, you want that, you find something to link them. And this is why NMF is cool. So numerically, NMF is this optimization problem that is given a matrix M is given, and you want to minimize the distance between M and the product W and H such that the distance in terms of forbiddance norm is as small as possible. In the best case, that means the distance is 0, then you get exact factorization. And of course, because it's NMF, so you have the non-negativity constraint. Non-negativity constraint means W and H are element-wise non-negative. In a more general sense, you can have other regularization. For example, you can have a G function representing other regularization, for example, orthogonal between column W, or something called unimodal in the column W, which I'm going to explain soon. And other constraints, for example, you want the W, the column to be normalized to 1, or you want some other fancy normalization. And in this talk, because this W and H larger than 0 appears so often, I'm going to skip it. I'm not going to mention it. I will just hide it to have some space. But you have to in mind, this is always exists. So now I will jump this detail I'm not going to talk about because these are just some details that are not so interesting and eye-catching. For details, you can read the thesis. So let's go to the most important, interesting aspect of NMF, that is the geometry. Because you are having a data that is non-negative and your factorization is non-negative. So here, linear combination become conic combination. So geometrically, you have a cone geometry. That is, for example, you are given matrix M, and you draw all the column of M, plot them as the data, then you get the blue rays or blue points. Because they are non-negative, that's why they all spread from the point 0. And because now you are having a conic combination for the data point, because W and H here, the H is non-negative, that means it's a conic combination of column of W. So that means you are trying to find a cone to contain all these blue dots. For example, in the diagram, the red cone containing all the blue dots. But at the same time, the green cone actually also containing all the blue dots. So you can see, if the question of NMF is asking just find a cone to hold all the data points, you can see there are actually infinite number of ways you can do that. You just need to find whatever cone that is larger than the red one or smaller than the green one. And any cone in between the red cone and the green cone, you can use it as a factorization. Then this naturally gives you an idea. How about finding the cone that has the smallest volume? That means this comes to the thinking of minimum volume NMF. That is, you want to minimize the distance between M and W and H, plus now you have some volume measure that is notated by the function V. And of course, you can add other constraints, but they are just details. So then you will have a question, what is volume? Well, there's a theorem saying that the determinant of the gram takes square root is actually the volume of the convex hull of W times H in the column space of W, blah, blah, blah. So what does it mean? Basically, it means the following. You can think of this like this. Let's suppose you have some columns of W. You want to find the volume. Then what you do? First, because volume is related to the length of the polygon in the W, so you will take what? The length of the first column, W1, take the norm, 2 norm, and then let's say you take the square. And then you have the remaining column. Now for the second column, you don't want to double count the length that is contributed by the first column, right? So what you will do for the second column, W2, you will multiply it by a matrix P1, and then this matrix P1 orthogonal means this is an orthogonal projection to the span of the first column. That means you are removing the contribution of W1 in W2. Then that means the second norm in the equation is exactly the length of W2 purely independent of the first column. Then you can do the same thing on the third column. You remove the contribution of the first and second column from the third column, and then you take the norm square. And you do this all the way. So this is actually the length multiplied by length squared. So that's why if you take the square root, you get the volume. So this is the geometrical interpretation. And if you want to have a diagram, basically it's saying that you have a parallelogram in high dimensional space. Basically, it's like you have a parallelogram like this. Let's say this is first column, this is second column, then the size will be something like this multiplied by this. Of course, it's not directly this vector dot product. This vector is like this vector dot product with this vector subtracting the contribution of this vector, so more like this. Yeah, that kind of thing. But this is not important. The important message is here is that the volume is actually something related to the determinant. Then there's other things. Linear algebra say that determinant function actually equal to the product of the singular value square. And this gives you some idea. Because if you minimize the determinant of W transpose W, it's equivalent to minimize the product of the singular value square, then actually this may not be a good thing because the expression, the product of singular value, is actually dominated by the dominant largest singular value. So that means it's quite sensitive to the largest singular value, but you are ignoring the small one. So maybe you can consider other functions. For example, you put a log. So that's why you have the log determinant term. And then the log determinant term, you see there is a delta is because this is just to make sure there is lower bound. Because if there is no delta, when W is rank efficient or W is 0, then you are doing log 0, which is negative infinity. And you are doing minimization, you don't want that, so you put the lower bound delta here. And it turns out tuning this delta is a serious issue in the minimum volume NMF. And then there are other functions. So in terms of theory, colleagues and I, which the colleague is sitting here, derived this theory, basically saying that if you have an NMF data M generated by hidden W and H, and then you have some condition. The SSC stands for sufficiently spread or sufficiently scattered. Basically, it means the data points are not concentrated to one point but spread out. Then, if you have all these conditions, then you solve the minimization problem. The exact solution will be unique. So this justifies why NMF, mean-mode NMF can be used to solve practical problem, because if they are satisfied, the conditions are satisfied, then you have the unique solution. So what is the illustration? I'm going to show you a figure. So from the figure, the GIF, you can see that now I have some data point. This is a 5-dimensional data point. There are 2,000 points, and rank is 3, so we have 3 dots. Basically, it shows that these data points in black are generated by 3 red dots in the corner of the triangle. Your task is given the black dot, find the 3 red dots. And the blue dot here is the estimator. That means it's the one to estimate the red dot. This is how the trajectory of the point moves according to mean volume NMF. You can see in the beginning, the triangle, the blue triangle expands. And then because of the regularizer, it cannot expand indefinitely. So it will come back and then it will try to fit while minimizing the volume. So ultimately, it will fit the red point. So this is the idea. And Well, although this is a 5-dimensional data, but this is actually a 2-dimensional projection, but the idea is the same for high dimension. So I summarized, that is, I talked about something called mean value NMF, but I didn't talk about the details. So you may wonder why study mean value NMF. Of course, they have application. The first application is geography application. For example, hyperspectral image. This is a scene in somewhere in California, that means real place on Earth. And then you can see in the photo, there are 4 different types of material: water, soil, road, and vegetation. So what is a hyperspectral image? It's like this. A photograph is actually an image taken with respect to visible light. Hyperspectral image, it just means you take a photo with respect to X-ray, gamma ray, radio wave, etc. So that actually is just a photo. And for different kind of material, they have different absorption spectrum. Basically, it means the behavior of the object react to light. For example, an apple is red is because when you shine the light on it, it absorbs other light other than red and it reflects red. So you have a spectrum on apple. So these are the spectrum for the full material. And the goal of the hyperspectral unmixing is that given this data, try to decompose the image back into the individual component. So it is like an image segmentation. So how NMF achieve that? Very simple. You have the data. Let's say you have data with respect to wavelength number 5, and then you vectorize it, then you form a row column, and then you stack all the column row into a matrix, you get an M, and then that's here you run NMF, and then NMF will give you W and H. For the H, actually is an abundance map. That means you get a representation of how many components of this material in this corner, in this pixel, in this geographical location. And W is the absorption or reflection spectra. So this is a illustration. For example, you have this scene, and then you can decompose it into 4 components because you see that there are 4 components. So you say there are 4: water, vegetation, dirt, and road. So the first row in the decomposition is by something called mean volume NMF, and you can see it is already okay good. For example, for the water component, you can see on the water region is very strong. That means it identifies the water region. And the last row in this figure is from a reference, which is they do something called sparse NMF. And here, because they do sparse NMF, their map sometimes is a little bit cleaner. So I was thinking, what about sparse mean volume NMF? That's what the middle 2 column is doing. The second row is actually 2 sparse mean volume NMF. And for this example, it is the best one. For example, when you look at the water component for the reference, you will see something outside the water region have some response, but for the 2 sparse, it's perfectly clean. That means there's nothing outside the water region. And also for the last component, the row. For the row component, both the reference and the 2 sparse model are very good, but if you look at the seashore, the 2 sparse is very strong. It basically captures the whole seashore. And actually, if you look at the Google map and look at the real picture of this scene, you can see actually the seashore has some stone there, which exactly telling you, yeah, there's actually some material in the seashore. So here is another example. This is for Samsung data, and I don't know where is it, but basically just somewhere on Earth. So you look at this figure, you see there are 3 components: vegetation, water, and ground. So you may think that, okay, you decompose it with rank R equal 3. But what about if you try R larger than 3? You get this result. The first 2 rows showing the result if you decompose it using R larger than 3. Then actually you can see that you get other different type of trees, different type of soil, and then you can then recombine them to get the 3 components. And that is what's shown in the last 2 rows. And this actually handles something called spectral variability. Basically, it means that there are different kind of tree, different kind of water, different kind of dirt. There's not just one type of water, that is. So this is to illustrate mean value NMF is useful to solve this problem. And then these are the details. I skipped it. For example, I didn't talk about how I run the experiment, what is the setup, how to tune the parameter, but they are not so interesting. So the next one of the application is audio source separation. Basically, you have some audio signal. This is merely have a little length. The first row is the score. And then the second row is basically the representation of the data in time domain and in time frequency domain. And the last row is the decomposition. From the score, you can see there are 3 notes. So you are expected to have 3 components. That is the C note, the D note, and the E note. But here I run min-raw NMF with R equal to 5. And you can see it extracts the 3 components. And it also extracts something called Hammer noise and a redundant component. This is actually important observation. It means that you, in general, in application, you don't know the factorization rank R. But in this case, this is saying that that's okay. You just use a R that is big. If the R is too big, the model itself will automatically cancel out those redundant components and set them to 0, and you still get a good result. So this is something like automatic model order selection. So for illustration, I'm going to play a music. So this is called a do-do music. So this is the signal in the time frequency, time domain and time frequency domain. This is the spectrum, and I zoom it. You can already see the pattern. Go up, go down, go up. And then what you do NMF. This is the result of NMF. This is the decomposition. You see, it matches perfectly. So these are the estimated source. Now you have 8 sources. So you can see this is one of the nodes. And then a C node. And then a D node. This is the funniest one. This is actually the called a hammer noise. That is the activation of the node. So you can see the min-raw NMF on audio decomposition actually give you meaningful results. And this is another illustrative example. This is even more complicated music because Mary had a little length, or the do-do music is so simple. This is from Johann Sebastian Bach, the first prelude, number 1 in C. And then this is the first 2 measures of the music. This is played by a real person, real recording, and then I decompose it into, let's say, I don't remember 13 or 14 R. And then you can see this is the row of H. It corresponds perfectly to the note. And this is just to illustrate it works. Then the question is, wow, it looks so magic. How can it be? So here is the illustration why this approach works. So basically from the top left, you have the input, which is the time series xt. What's happened? This is a time series, is a vector, it's not very interesting. So you do a time frequency transform represented by 5. And this gives you a matrix xft. This is actually a complex matrix. So in order to do NMF, actually you need to do complex NMF, but this is out of the scope of the thesis. So I just do real NMF. What I do, I split this complex matrix into 2 parts, the real and the imaginary part. The real part is called the amplitude, and then I do NMF on this real matrix, and then I get W and H. Because I do a R component NMF, so I have R source, and then what I do, I just turn this R source back to the time domain. That is, I take this R matrix C, they are rank 1, and then I multiply back the phase, and then I do the inverse time frequency transform, and then I get the vector Y1 or YR. And they are those music you heard previously. So in order for NMF to work in this aspect, actually there are quite a lot of assumptions you need to do. And other than that, the data fitting term is actually not the Frobenius norm, but something called data divergence. In the thesis and in this presentation, I'm not going to talk about the data divergence because that's actually the main work of my colleagues. So I just treat here as an application. So in order for the NMF to be applied on the audio data, actually you have to satisfy a bunch of assumptions. And violating this assumption actually leads to new research opportunity. For example, you have to assume there's no time delay in the mixing. This is definitely true for audio data, but this might not be true for other data. For example, for EEG, because there will be a time lag in the EEG. This is well known. And then, of course, you are shown linear mixing model. That means everything is linear, happy. But in reality, maybe not the case. For example, if you have multiple reflection, then it's definitely not linear. But then that means you have opportunity to consider other NMF. And for the source, you are shown they are balanced. If there is a source very loud, actually your microphone is going to get saturated and you just get a bunch of 99999, then you cannot do anything. In that case, NMF, I don't think it will work. You need to study statistic approach. And then, of course, you assume other things. For example, they're additive, they don't cancel each other, and then they are well approximated by rank 1 matrix, blah, blah, blah. So these are the assumptions. And I'm going to talk about the A6, which is called consistency. So what this means? Basically, this is related to the audio or time frequency itself. You have an X, you apply time frequency transform, you go to a region here, you get a big X. Actually, this big X lives inside the gray region. This is the region where you have the time frequency transform from real data. That means this gray region corresponds to a real signal in the original time domain. And then here's the thing, if you do NMF in this X, actually it's possible. Either this X will go to the Y, that means the decomposition on the V give you W1H1, or either the V decomposition give you W2H2. You can see that one of the points is inside and one of the point is outside. This actually is the problem. If the point is really inside the gray region, when you do the inverse transform, actually it go back to a Y, a small y. Actually, this is okay because it really corresponds to a real signal. But if it goes back to the Z, small z, actually in this case, that means you are having some artifact. That means actually Z is actually Y plus something. Let's say artifact is A. So here is the problem. If the solution is actually outside so-called consistency region, then actually this solution is not making any sense unless this Z is very close to Y, or in other words, the artifact is very small. For the audio data I use in the thesis or in the illustration here, because the signal is very strong, so I can be happy to say that this is not a problem, because the signal to distortion or signal to artifact ratio is so large, so it's okay. But of course, there will be some distortion or artifact. That's why when you hear the audio just a moment ago, for some sound, it does not sound so natural. There's a little bit rare. Maybe that's because of artifact. But as long as the artifact is small compared to the signal, then I would say this is okay. But this is not the case for other research domains. For example, in the EEG data, the brainwave is well known. The brainwave is so weak. So they may have a very serious problem on this issue. And yeah, but for those research, I didn't see they talk about this. So this is a summary. I just talk about the audio data and the hyperspectral data on NMF. And I didn't talk about, for example, the audio processing itself in details and what is the beta divergence, how do you solve it, and how to do this experiment, blah, blah, blah. These are just some minor details. So then I finished part 1. Now I'm going to do part 2, which is called unimodal NMF. So what is unimodal? Basically, it means that your vector looks like the vector in below. You have a rising peak and then a falling down peak. And notice that in the figure here, the red dot actually represents the P. So what is the P? Basically, the P is the position such that this system of modulate inequality is true. Basically, it's increasing, and then up to somewhere, and then it decrease. So the P is the position of this kind of behavior, the change of tonicity. And the P is not unique. You can see for the second example, there are multiple P. And for the third example, all the values are possible P. So what to do for this we can do is to characterize the behavior. That is, if X is unimodal, we can say that it will satisfy this system of inequality. That is, on the rightmost side, you have a bunch of inequality, and you can see that this is actually just x1, x2, x2, x3, x3, x4. So actually you can represent this stuff as the inequality using a big matrix U. So the U have this structure. Street is just a bunch of 1 and -1 and 0. And the position of this 1 and -1 is dependent on the P, the index. So in this way, you come up with a model called unimodal NMF. That is, you just solve the NMF problem, but you have a new regularization. That is, you have a constraint. The W now is not non-negative. The W has to multiply something, and then the whole thing has to be non-negative. And well, for the H, you stay the same. H is non-negative. Here, Wj is the column of W, and Hi with the superscript is the row of X. And because this problem, you have the P as the variable, so it actually has some integer variable on it. To solve this problem, because you have integer, the easiest approach is to solve it by brute force. That means you solve this problem by trying all the P for all the possible P, and then you find the one with the best fit and take it as the P1 or P2 or P3. This is brute force. And of course, brute force is stupid because it takes time. So there are lots of improvements. For example, accelerated projected gradient design, peak detection, and multi-grid. So what is accelerated gradient design? Basically, just you use the fastest method to solve the problem, number one. Number two, peak detection means if the data is very good, for example, the data have just 2 peaks, then by eye you can see where is the P, so you don't even need to run brute force. But if the data is not so clean, they have multiple peaks, then you can run some peak detection algorithm, but have some built-in algorithm on it. So this is just trying to say you can try to guess the P without using brute force, or reduce the possible search space of brute force. And lastly is multi-grid. Multi-grid is actually the funniest thing. That is, you have the data that's very big, you just make it smaller, and then you brute force on the small problem, and then you go back to the original problem. Because if your problem is small enough, you can just brute force it. You don't care about the cost for a small problem. And why do multi-grid? Why not PCA? Why not sampling? Because multi-grid preserves unimodality. Basically, for example, you have a multi-grid. That is, you have a vector X. Multi-grid is saying that you, instead of working on X, you working on Rx, and R has this structure. And there's a theorem. If the X is unimodal in the position P and P is even, then the solution vector Y after the compression, it will be still unimodal, and the P just shift at most one position. That means you can still find the P of X if you know the P of Y. And this is to justify this theorem, which is to justify the use of multi-grid. And you can just keep making the problem small until it's small enough. Then you run the brute force, and then you get the solution, and then you project it back to the original problem. This is much faster. And then regarding this model, I have 3 preliminary identifiability results. Preliminary means in the sense that they are not complete. A complete identifiability theorem means you have a model NMF with any number of R, and the vector in the NMF can be whatever you want. Then you can have some uniqueness guarantee. But here, no, I have some condition. For example, the first one saying that the vector has to be strictly disjoint. That means there is a 0 between the support of 2 vectors. And then the second theorem is saying that it is not strictly disjoint, but if they are something called independent sensing, that means if they are overlapping each other, but they appear separately in the data, then you still can recover them. And the last one is quite interesting. It's just saying that if you have 2 unimodal vectors for R equal 2, you always get unique decomposition, because for 2 unimodal vectors, even they overlap, they cannot be expressed by, they can only have one unique expression by 2 other unimodal vectors. So this is an experiment illustration. You have some data that is W true generated like this, and then I make a matrix M building a random H that is 6 by 100, then you get this M. And then I run unimodal NMF with doubling the position of P. So for example, for this guy, the blue one, the P is at 20 something. And then for the red one, you can see because it had a flat top, so there are a lot of P is possible. And then I do the NMF. below the plot in time, runtime for the NMF, unimodal NMF with 1 grid, 2 grid, and no grid. Black is no grid, and blue is with 1 layer grid, green is with 2 layer grid. Of course, you can do 3 grid, 4 grid, but this is enough. So you can see that in terms of the cost objective value, the decrease with the grid is actually much better than without grid. And here I take into account the time you run on the small program. So that's why the first dot in the blue and the green is so far away from the time 0. But for the black one, they are evenly distributed. I mean the grid size. And this shows that with grid, you can muchly improve the convergence time because it has 5 times or 3 times improvement, depends on number of grid. So it tells that if you want to solve unimodal NMF, you have to use multi-grid. Otherwise, the time is too high. And this also concludes that I don't need to compare with other existing approach in the literature because they basically have the same complexity as the method without grid. So that's why this is enough. And then this is another example. This is from real data this is actually from real data of Belgian beer. And this is called gas chromatography data. And I'm not going to explain what is gas chromatography. You can go to the thesis to have a look. Basically, you can take it as some peak and you want to decompose it into individual components. So you can see that for NMF and SNMF, which is called stepper NMF, you cannot do the unimodal stuff because you can see they have highly mixed up peak. But for the unimodal NMF, of course, they are unimodal. That's why you have individual peak. And then you can then go to data book and check where is the peak location, and you can identify, oh, this have this chemical, that have that chemical. But for NMF and SNMF, you can't. For example, for the first component in SNMF, you don't know what are they because you have 3 peak. So you have to check if the first component is actually 3 things combined together. But then this is not so good. So this is the unimodal. And now I move to the last part, which is mostly algorithm. And the algorithm is very simple. Basically, something called extrapolation method called her. And basically, I just use it to solve NMF problem or NTF problem. What is NTF problem? Basically, just NMF in 3D, in 4D, in 5D looks like this. And the key idea in the algorithm is basically very simple: is no matter what happens, you just extrapolate it. Because extrapolation sometimes give you good thing, sometimes give you bad thing. But when the extrapolation give you bad thing, then you just abandon it. Then you may wonder, if you do extrapolation regardless of the situation, that may be expensive. That's how the thing works. You make the extrapolation very cheap. This is the key idea. That is, you make the extrapolation very, very, very cheap. So no matter what situation, you just extrapolate it, then you will gain speed up. Because the extrapolation speed is cheap, so that's why even if it's doing worse, you abandon it, you don't lose anything. So why extrapolation? It's just because this is a natural phenomenon, natural thing in optimization. When the objective function, the level set or the landscape is spherical, then the point moving to the global minimum will be in a straight line. This is actually gradient descent on a quadratic function. And if the landscape is getting more and more elliptic, you can see it's starting to zigzag. And zigzag is that thing because why don't you just move from the starting point to the solution point directly? But that is not the case. You cannot avoid it. So that's why you do something called extrapolation. Extrapolation is trying to counter this effect. That is, you have 2 sequences instead of 1 sequence. Previously, you only have x. Now you have x and y. And you are using y as the extrapolation point. You basically just take y as xk plus 1 minus xk. This is the direction. And then you move along this direction for beta amount. Then you get a y. This is like the idea. So this is the overall framework, but this does not tell you a lot of things. So this is better. So what is this? Basically, let's say you have n variable. They are a1, a2, a3, up to an. So this is actually the framework. First, you update a1. Up means update. And after you update a1, you go to something called xa1, extrapolate a1. And then you project a1 because you have the constraint. If your problem have no constraint, you don't need to project. So basically, it's like update A1, extrapolate A1, and then project A1, and then you move to A2. So it's like update, extrapolate, project, and you keep doing it until the last block. This is block coordinate design. And of course, there are other algorithms. This figure also captures the essence. For example, there are some methods you update all the block at once. Then you don't move from update to extrapolate, but you move from update A1 to update A2, and you do all this in one step. So this is then actually this shows a lot of potential in terms of algorithm design. That is, why update and then extrapolate, but why not update and then update all and then extrapolate all? And also how to link between the steps. That is the design of the flow of the error here. Actually, there are so many possibilities, and no one can tell which is best. So this actually gives you lots of research opportunities. But in the thesis, I just consider this special case for the tensor one. And for the matrix case, actually, because only have 2 blocks, so I also consider other possible linkage. And the result is very simple. It just works. So now go to thesis. Let's say you go to page 114. Here, in 114, this is the data set on NMF. These are just some famous data set. And then these are some famous text data set, and they are very sparse, and for the image, some of them are very dense. And the conclusion is just to tell you that no matter what, basically, when you do extrapolation, it just give you better. For example, this line, the blue dashed line, is AHARS, and then you see for the line below it is just the extrapolated variant. So, and you can see there are a lot of factors having this kind of behavior, so I'm not going to repeat it. And then now let's jump to the tensor case. And if we jump to the tensor case, the same thing happened. For example, let's say we now move to page 125. This table shows you almost different kind of test situation. That is, the tensor have 50 by 50 by 50 and rank is 10. And then different unbalanced size. That means the tensor is a long cube, and then a long sheet, and then a long big cube, etc. Or even big data. For example, this is 10 to the power 4 times 100 times 200. This cannot be low in a single CPU because this is too big. So that's why this one needs further processing. But the conclusion is the same. As long as you do the extrapolation with the HER framework, it just works very good. And yeah, basically the figure just like this. This is figure 7.13. The blue one is the method without extrapolation, and the purple one, no, the orange one is the method with extrapolation, and this is 20 repetition, 20 trial. So you can see for the all 20 trial, for the AHARS method, the with and without extrapolation already have a 6 order of magnitude different at time at iteration 200. This is iteration and this is time. And this kind of graph just appear everywhere in the thesis, so I'm not going to talk about it. So in conclusion, the extrapolation, the idea is you just extrapolate regardless of situation as long as the extrapolation is cheap. So this is the thing. I didn't talk about the detail of the algorithm design, but this is the idea. So lastly is a summary of the contribution and almost the end of the presentation. So first, about the summary, as the title suggests, is model, algorithm, and application. In the model, I consider 2 models, min-vol and NU. Min-vol means minimum volume, and NU means non-negative unimodal. And I have new model and new identifiability result, and then experiment showcase the algorithm works better than existing one, and that's it. And then on the algorithm part, basically is the acceleration framework. It can be used to solve NMF, NTF, CPD. Actually, I also try on other models, for example, completion problem, but I didn't put in the thesis. It also works. And then the idea is here, just accelerate anything, and you just accelerate without considering anything. You just keep accelerating it. The key idea is if the acceleration step is cheap, then you don't get any loss if the acceleration doing bad thing. And the result is telling you is good. And lastly, about the application, just 3 things: geography, music, and chemistry. Of course, you can even apply it in a broader application. For example, you don't necessarily working on chemistry data. You can even work with the dynamics of infectious disease. For example, is COVID-19, the number of case is unimodal? Of course, it's unimodal. That means you can use it for NUMF and you can detect it by saying you can know the baseline of the increase of case, and then you can also extract the sudden peak that is due to, let's say, external factor. And then, of course, for music, you can use the same algorithm on EEG. And then for the hyperspectral imaging, of course, you don't really need to apply only on hyperspectral image. You can use it on other data, for example, text data. And this is the end. This is the thesis available online. And I have to mention, very importantly, just after I printed it, I found some typing mistake, sorry. So there is an errata, but just typing mistake does not hurt the theory thing. And this thesis is the ensemble of these 10 works, and last one is just new. And that's the end. Thank you very much.